Well, guys, today we have Travis here speaking. Travis is from Continuum, or is it Anaconda?
It's called Anaconda now.
It's called Anaconda now, but Anaconda is the team that builds Anaconda and also manages Jupyter, I believe? Jupyter Lab. So Travis here has been the creator of NumPy and one of the founding members of the SciPy team. So I'll let him take it from here.
Great. All right. Thank you, Hashi. It's a pleasure to be here. I really love coming to universities, colleges. I still feel an academic at heart. I spent many, many years, got a PhD at the Mayo Clinic. I'll talk a little bit about that. Kind of my subject today is, I didn't quite know what to talk about. You're all a bunch of aspiring adults. I wondered, I thought we'd mostly have students here. So let me just raise a hand. How many undergrads do we have? Undergrads? Awesome. Graduate students? Any graduate students come out on a Saturday? Right? It's working busy on your research as well. Any PhD students in those? No PhD students, all master's degrees? One PhD student, awesome, yes. I got a PhD, some of the best times of my life. It was definitely a challenge, but honestly, the things I learned during that phase of life, I think have helped me, helped direct me for a long time. So as I thought about what to talk about, I decided I'd talk basically about Anaconda and the breadth of tools that are around that, focus on a couple of open source projects that there's a lot of things we've been doing. So I'll focus on a couple of open source projects I really think you should know about that really help to, I think, help people really take AI and machine learning where it needs to be. It's actually not about the algorithms that these help you with. You'll hear probably studying some of those algorithms, a lot you're going to do to bring us forward into the future. We're going to talk about the systems around those algorithms. And talk about communities and how in that process I kind of found this concept called Ikigai. There's a TED Talk on it, there's web searches on it, you can find out a lot about it, but I think it's a really nice concept for finding meaning in life. You know, what's your purpose? What you're trying to accomplish? When I encountered this, I thought it really summed up kind of how my journey through academia, to starting companies, to trying to start and create communities to help many more people find Ikigai. So that's what we'll talk. A little about me. I've been a part of the Python for data science community. That's essentially where my home has been for about 20 years. I didn't start thinking I would do that. When I was a young student as an undergrad, I studied electrical and computer engineering because I loved physics and I loved electromagnetism. I loved Einstein's relativity and how special relativity really came from electromagnetics. Maxwell's equations kind of implied special relativity. Loved it. I loved really the epiphany that created in me. And so, but I also had a family. I got married young. I have 6 children now. And I had married when I was still an undergrad. And so I always thought, how am I going to support this? I can't just go and do physics all my life. So I went into electrical computer engineering, thinking that would help me get a job later. So, but that journey eventually led me to biomedical imaging. After electrical computer engineering, I decided that I was doing a little bit too much. I loved signal processing, loved estimation theory, loved advanced probability, but ended up realizing that most of my friends were getting jobs at Raytheon and kind of Boeing and other places. They do a lot of great things, but I didn't want to necessarily build missiles. Not that defense isn't a good thing, but I wanted to take my efforts and apply them to biomedical imaging. So I went to the Mayo Clinic. At the Mayo Clinic, that's where I encountered Python. Trying to basically do 5-dimensional derivatives, I found Python was easier mainly because it supported floats. And I'd done enough programming that I ended up finding my way, kind of what I was good at was point arithmetic and dealing with large array processing. So I ended up exploring the numeric world that was there and kind of started the SciPy project. I'll talk a little bit about that if we get to it. Since then, my journey, that sort of journey into software to do science led me to the open source community. One thing today, we all know about social networks. Facebook, Instagram, I'm not even sure what people do today, right? Snapchat. My kids do experience the internet in a whole new way than I did. In fact, when I didn't have a cell phone until 2006, right? So a lot of this happened before, but I had a computer. And we were doing BBS, bulletin boards when I was young. And the internet kind of came around as I was graduating my undergrad. That was when schools had them. What's that? Back when LimeWire existed. Yeah, LimeWire was good stuff. But what happened is when open source kind of, really Linux took off, and then all the open source took off because of the connectivity the internet provided. Those were the first communities that emerged, global communities that emerged, and our interactions were over whatever means we could. Email, little web pages. I had some really crummy web pages I put up just to distribute software, and then we connected. And that connection with each other really led to kind of transformation of software, and we've seen that transformation take place for the past 20 years. So back then, there was sort of a, no, open source can't work because big companies have to do software, and now all the modern AI tools, all the modern machine learning tools are all open source. Everyone recognizes that, and that's not to say there isn't room for proprietary software. That's a deeper subject. That's another subject. But the infrastructure, the foundations are going to be open source, and that revolution happened. That's when I was in the middle of that. Before I started writing, and then as a professor of electrical computer engineering, I wrote NumPy. And since then, I've been sort of trying to figure out how do I make this thing that I love so much a bigger part of my life and support my 6 kids at the same time. So what's been happening lately? It's been an amazing explosion, actually, over the past 5 years. Python, and PyData in particular, is just growing exponentially. Now, I like to think it's because of Anaconda and the company I started, but I actually know it's because of the great work of machine learning tools, the analytics, the AI work that's been going on. So much interest is happening. It's basically Alexa and Google Home and Siri and the promise of artificial driving cars, and the promise of radiology determining whether you have cancer or not by taking pictures of your skin and sending that in. That promise is leading a lot of people to be enthusiastically pursuing artificial intelligence. Of course, when you start to do that, you realize I got to do some algorithms. There's a lot of math here. There's a lot of data here. How am I going to handle all that? If you're sitting there writing for loops in C#, good luck. You're going to be around for a long, long time. So people started picking up tools. The best way to build something, as Newton said, is to stand on the shoulders of giants. And society really progresses that way. I'm not a big believer in single, even though we have our heroes, we have our Einsteins, we have our Newtons, look deeper into the situation, you realize they were really just popularizing a concept that was emerging already. That's true all the time. What's happening now is to popularize those concepts that are emerging already, you have to bring them together, stitch things together. So I think artificial intelligence has led to this, and the explosion of big data and the desire for getting insight out of that data has led to this. So who here knows about the Python scientific stack? How many, do you have any Anaconda users in the room? Only a few. Wow. Okay, what do the rest of you guys use? C#? How many programmers, so how many people that program do we have here? Okay. And of those programmers, how many are Fortran programmers? Fortran? All right, represent. There we go. Fortran, many of my friends still believe Fortran is the only way to really coax a machine to do what you want it to do. What about C, C++? Okay, got some hardcore C++. Okay, how about Java? Sorry. Scala? Scala? No, I'm a little rude. There's a lot of great things about Java. It's sort of the overreaching that I get a little annoyed with Java. I particularly like Scala. If I had to use the JVM, I'd probably write Scala. Clojure, functional languages. Any functional fans? OCaml, Haskell. Anyone willing to admit their Haskell? So I really like Haskell, OCaml. I love studying those. I've never used them in particular to do something useful. Okay, so Python is kind of new to a lot of you folks. So raise again those who've used Python. Okay, a lot of people use Python. All right, so it's not that unfamiliar. But really, there's different worlds in Python, right? That's one thing you have to understand. A lot of people miss the Python ecosystem and how big it is because they focus narrowly on one world. They think, oh, Python for system administration, or Python for web development, or Python developers, people who could use C or C++ but decide to use Python. There's a whole community of people out there that would never use C or C++. They would never use Java. They'd never use anything else. They're trying to get machine learning done. They're trying to do data science. They might use MATLAB. They might use SAS. They might use R. Right? Those people are the ones who have made Python grow so exponentially over the past 3 or 4 years. And that stack is what we call the Python scientific stack. I call it the PyData stack, NumFocus stack. It's really built around NumPy with core, and really at the core of that is a buffer protocol that allows multiple structures to communicate about data in a common way, to do array-oriented programming. And then you have Jupyter, which is a notebook interface that allows you to interact with interact quickly. You have tools like Cython. Cython is an extension writer for Python. The reason Python became so popular in programming in data analysis is because it was a glue language. It really helped glue Fortran code, C code, a bunch of code together, and then people could steer it. And did that pretty simply. Numba is a compiler for Python. I won't talk about it today. I could. It was one of the things we started. We started Continuum, now Anaconda. Numba is a compiler that takes Python code and produces C code as fast as Fortran, as long as you don't, fix the flags in your Fortran compiler. And then Dask is something I will talk about. It's a parallelizing Python. Very, very cool. Allows you to take Python code and the whole Python ecosystem and figure out how to scale it out to thousands of machines. So it's a very nice tool. On top of that, you have Pandas. Now, Pandas has really driven a lot of popularity for Python as a data analysis tool. Pandas is built on top of the array structures, like NumPy, and on top of that, it creates labeled arrays. Basically, imagine an Excel spreadsheet, an object in Python that is an Excel spreadsheet. You can get the rows, you get the columns, you can do joins, group bys, pivot tables, all very simply. And then Bokeh, Xarrays, Pandas in multiple dimensions. SciPy is a library that really got me started in that open source world, and I'll talk a little bit more about that later. Matplotlib visualization. On top of that, you get the tools that people start to use. Scikit-learn. Who's used Scikit-learn? If you haven't used Scikit-learn and you're interested in machine learning at all, just go conda install Scikit-learn and start playing with it. Go to the documentation and learn machine learning in an afternoon, basically by walking through the documentation of Scikit-learn. It's an amazing, you'll get a feeling for how machine learning works and how you actually can take data and fit it to an advanced model and do something in the direction of artificial intelligence. Understand just how accessible that is. Now, get the right data, that is. I mean, the key to really successful AI is the right data, and it has been and will continue to be. Then stats models, SymPy is a fantastic symbolic manipulation tool. It's gotten better and better and better. That's one of my sort of favorite projects in the ecosystem because who's a Mathematica user? Maple user? Right? There's some really cool things you can do with symbolic manipulation. Now with SymPy, you can do its integration works pretty well, the summation works pretty well, solve works pretty well. So it's really, really fun. And then on top of that, you have sort of industry-specific AstroPy, BioPython. There's a neuroimaging Python, SunPy. There's basically, no matter what domain you're in, there's probably somebody out there who's got a collection of tools on top of the Python scientific stack for doing that more easily in Python. So that really it's a feedback effect, of course. These network effects happen where the more people get together, the easier it is to share with each other, the more you can build on each other, and kind of the richer the ecosystem becomes. And that certainly has been happening in Python. It did not happen overnight. That exponential curve happened pretty quickly in a couple of years. But if you've ever read books that talk about exponential growth and how that works, there's always a period where it's not growing. It's still growing exponentially, but it's very small, right? And then eventually it becomes visible because of all the effort that happened back here. And that's been going on for 20 years, nearly 20 years, roughly 20 years in the Python space. So that's where we are. So Anaconda comes in basically as, great, the more this grows, and it's just exploding. There's over 80,000 packages on the Python cheese shop, used to be called, PyPI, Python Package Index. How do you get them all? How do you get all those tools? That was the problem we didn't start out to solve when we created that continuum. When we created continuum, we wanted to solve the data connectivity problem, like the next generation scalable problem. We wanted to scale Python, do applications in the web, and bring Python to big data. In the process, we had to solve the shipping problem, the packaging problem. How do you get all this stuff into people's hands? And if we did that, that became the most popular thing we did. So this is another way to look at Anaconda. So this is the way to look at Anaconda from a library package perspective, all the different tools in machine learning or analytics, distributed systems, web, scientific computing. Anaconda brings them all together. The other way to look at it is from a data science workflow perspective. If you're trying to do something with data science, if you're trying to do data science, what do? What does that mean? There are a lot of people out there who will draw diagrams about the process. I wanted to kind of step back and look at the whole process as a single item. It's a loop. It's actually inspired by something called the OODA loop, the Observe, Orient, Decide, Act loop that the military uses. this is the data to decisions and actions loop. And as you have decision actions, then you get more data. But as you get the data, it's not just having it, it's understanding it. And 80% of the effort people spend today is in that upper red part. It's getting the data, understanding the data. So cleaning it, moving it, putting it in the format they want, getting it into an understanding that they're looking for. Of course, most of us, when we're trying to understand data, we're actually trying to understand the world. Using data as a proxy to understand the world around us. And the connection between those two is models. And models can be generic, they can be simple. In fact, there are a lot of mileage for the past 60 years with very simple models. In fact, in most banks, they have models of your credit, of your account balances. And most of them are a pretty straightforward regression model, simple linear models. They're getting more advanced now. Those models aren't sufficient in order to translate your voice and understand it, the audio in your voice, to text so the computer could process it. Linear models aren't sufficient, so you have to have nonlinear models. At the end of the day, that's what artificial intelligence is a collection of nonlinear, more complicated models going from one set of data to an output you're interested in. The result, though, are the data products. There are reports, there are analytics, there are applications, there's tools, and then that feedback continues to build on itself. Anaconda, its purpose is to make that process simpler. Have the tools together, have a place, a foundation, a framework. I call it sometimes the OS of data science. I want it to be a foundation so no matter what hardware you're running on, no matter what you're trying to deploy to, brings the tools together. Now, we're not completely there yet, but we're getting there step by step. Anaconda helps bring all the tools together and then allows experts to really bring the future, bring out the future. So how many have heard of, many have heard of Elon Musk, and there's a few others that are really worried about the future of AI, the superintelligence. Now, actually, if some of you are really into that, I'd love to talk to you later, because personally, I don't understand the concern. I understand it conceptually. I just think we're about 100 years or more away from actually having that problem. Because of artificial intelligence, we barely understand how our brains actually work. We barely understand how to collect data sufficient to train the current generation of neural nets to do something realistic. And all they can do is really just nonlinear functions. Pull them together to actually reason, or to think, or to process, or to come up with new ways of kind of connecting together in a way that, not to say that's not impossible to happen, I think we're 100 years away. So right now, I think of AI, artificial intelligence, not as the sci-fi movies of having a robot that tries to kill me, or a robot that tries to take me over. I think of artificial intelligence as augmented intelligence. The real power in AI is going to be helping people that know what they're doing, have some connection to the world around them, helping them. They can do it faster, more efficiently, easier, by getting rid of a lot of the mundane things and helping to connect. I think we'll see a lot of that. We'll see a lot of simplification, a lot of the hard problems, mundane problems being taken care of by machines, and that will happen very quickly and rapidly over the next 5 to 10 years. And many of you will have a chance to do that. I see Anaconda as helping. I want Anaconda to be at the foundation of helping you do that work. So we've had some success getting the word out, and people have started to rely on this, especially kind of this growth in AI has really helped growth in Anaconda. We have about 2 million downloads a month if you combine our Anaconda, which is the full distribution, and Miniconda, which is just basically Python plus a package manager. And then from there, people can install and do whatever they want. So I think AI and machine learning will make your life better. I think everything eventually. There's still much to do. Now, this talk isn't going to go into aspects of AI and machine learning. If you're interested in talking about that, I've got a lot to say about that. My background is actually inverse problems. As a professor, I loved advanced probability theory, and I loved estimating information from data. And basically, artificial intelligence, machine learning is a corollary about that, focused kind of on algorithms and infrastructure and approaches to improving how we do that more quickly. But there's a lot of problems we have still that we have to solve. We have to connect data to models. Actually, just getting the data into a format you can deal with it. Models are still fairly sophisticated. We have all these machine learning libraries emerging with Torch and TensorFlow. But getting your data so they can be used by those models is still an effort. So that's an issue. Scaling model selection, how do you actually pick or create your deep learning model or just your standard model, your pipeline of machine learning model? How do you do that? There's a lot of evidence that we can automate a lot of that. We could actually just go and find a whole bunch of models and apply them to data automatically and then try to figure that out. That's emerging over the next 3 or 4 years. You'll see more and more of that. But then you have to scale model training. More data, more training. There's actually potentially numerical problems there. To scale model training as you get down and you're trying to optimize just a little bit more, you end up with precision problems in your data. So there's actually a lot of numeric work to do. There's a lot of just getting lots of machines talking together, doing something, work to do. Then you have packaging. There's 2 kinds of packaging. I'll separate because I think the web browser is a good way to think about this. There's packaging for development. So if you want to build a web application today, you got to have Node installed. You got to have tools installed so you can actually do the prototyping. That's packaging for development. Packaging for deployment. Now you have to deploy that. In the Node world, it's Webpack that is used to translate your development environment to a thing that can be imported by a browser. The browser then just points to your Webpack build code and then creates the solution. Mobile phones, Internet of Things, that's another area where you're going to have packaging for deployment that's different than packaging for development. I think that distinction is going to be more and more important. We need better interactive visualization of data, better tools, generally better tools for people with knowledge. So we also need people with knowledge. So one of the things you definitely need to think about is all the things you learn are going to help you. You do have to get very good at something to make a contribution, but you also need to be broad enough that you know enough about other things that the thing you're expert at can be applied as well. So at Anaconda, as a company, we're a company. One of the things that we do is, one of the reasons I started a company, I've read a lot of people talk about starting companies, and they often say, don't start a company unless you can't see the world without your company in it. That's definitely true. Starting a company is the hardest thing I ever did. I did a lot of things that potentially are hard. Starting a company, it was very hard. It affected my life, affected my health. I spent a lot of time on it. You're trying to wrangle a lot of things together, so why do it? Well, I did it because I wanted to see a world where people were paid to work on open source software. I want to see a world where a lot of people get paid to work on open source software, and that's happening more and more and more. But particularly in the open source software I care about. I saw NumPy, I saw SciPy, I saw tools like Pandas getting written, but nobody was actually being paid to work on them. They're just written by volunteers. SciPy emerged from my volunteer time. It came because I put my PhD on hold for a year. My wife was home with 3 kids and thought I was working diligently to get my PhD done, and I was. But I really got excited about this opportunity to build SciPy and the opportunity to pull libraries from 4chan and other places into and make them available through Python. It took me about a year to get that started. I look back at that, did that really help contribute to my PhD thesis? Nah, not really. But it definitely contributed to my life. And I really, you do that. You make those trade-offs sometimes. And that's an important part of life. So at Anaconda, it's always been a passion to build more open source. So we've done a lot of things, but they're kind of grouped into these 4 areas at Anaconda. So scalable computation algorithms, how do we scale? And there's 2 projects I'm highlighting here. I'll talk about Dask today. The 2 projects are Numba and Dask. Numba is the Python compiler. It's really cool. You can take Python code, run it on a GPU. If you're actually interested in compiler theory, Numba is an accessible compiler. It's something you can look at because it's staged. And you can look at how it works to translate Python bytecode into a representation that then can be translated to LLVM, and from there to GPU code to CPU code. Dask is a scalable library. Conda is at the heart. Conda is about deployment, reproducible data science. It's about the packaging problem. And we've got the packaging for development problem, I think, pretty well in hand with Conda. The packaging for deployment, I think there's still some progress we're going to be able to make. I'm not going to talk a lot about data virtualization and access. This is an important area, how to get data in. And then user interface and data visualization. We have a lot of mature projects around here. I'm going to talk a little bit about Jupyter Lab. Who uses Jupyter? Again, a few people use Jupyter. So Jupyter Lab is the next generation of Jupyter. It's basically the notebook built on a better foundation so it can scale and be extensible. So Conda. Conda is a package manager. How boring is that, right? A lot of things in life actually to help the world, you got to do things that are boring. That's actually probably one of the lessons that you definitely have to recognize. What Conda is, though, as boring as it may be, no matter where I go, I get a lot of people going, thank you for Anaconda. Thank you for Conda. Thank you for helping making my life easier. I can sum it up in one concept. While I was writing NumPy, one of the things I didn't realize was how hard it would be to change NumPy because of everybody building on top of it. There wasn't good package management in the Python ecosystem. And so what that meant is people would spend days setting up their environments. And those environments would have NumPy at the foundation, and they'd have like many, many other packages on top. And so if NumPy changed, and the rest of the libraries didn't work because the API changed, the ABI changed, if they had to recompile or reinstall, I heard about it. People would get really upset because it was a lot of work for them, and there wasn't good package management. So basically, days of work every time a new release of NumPy had to change the ABI. So what happened is the ABI of NumPy didn't change, even though there were some real warts in there, things that absolutely should have changed. They didn't change, and they couldn't change. They created all kinds of problems. So now with Conda, it makes no sense. It makes no difference. You can destroy your environment, recreate it in a matter of seconds. So it's not a problem at all to change ABIs because you have a dependency management that can track that and install the updated packages made available by other people in the world. So Conda really came out of some of the problems. In fact, if you look at SciPy, which is the first project I did, SciPy really was a distribution for Python. It was sort of all the cool tools that somebody who's doing at least the science I cared about, but then as the community grew, the science others cared about, all they wanted to kind of in one library. But it became really unwieldy. The problem with a big library is you can't coordinate across that many people to decide how to do things. And so, open source is better handled in packets, in chunks. People working together on their small project, and then tools integrating them together. SciPy was a big monolithic enterprise. It needed to be a bunch of smaller tools. Without package management, couldn't do that. So Conda really is a package manager. It's like Yum, apt-get for Linux, Macports, Homebrew, Finks, and then on Windows there are actually some package managers too, Chocolatey and Newbad. Most people aren't very familiar with them. Conda is a tool like all of those, but it also adds sophisticated environments, software environments, kind of mini containers, so you can actually modularize your work, share it with other people, reproduce it very easily, and have a bunch of different environments on a single machine. I'll go quickly over this. Basically, Conda install a package, Conda search for a package, Conda remove a package, Conda create an environment, and it's got some more advanced command line tool. There's also a GUI if you install Anaconda called Anaconda Navigator that has a graphical user interface for managing your environments and installing packages as well. One of the key things, if you're not aware of Conda or using Conda, take a look at it. It can manage more than Python. It can manage Go, Node, Java. There's a community out there that has Perl, CPAN, manages R. It's actually quite possible to manage and reproduce a lot of software. So definitely, advice number one, try out Conda if you haven't. It'll make your life easier. And that's an area where Tyler worked, actually. He's here. And, I have a story about him. Not too bad. No. Just part of the team. Dask, this is designed to parallelize the Python ecosystem. Paralyze it. And parallelize it. Dask really delivers on the promise, the real task we had when we started the company, to scale NumPy. One of the things NumPy is great at is arrays. NumPy lets you do array computing quickly. Array computing is probably best summarized by a conversation I had with a gentleman who was using Groovy. Anybody use Groovy in here? Groovy is one of those higher level JVM tools. It's kind of a scriptable JVM. But what he was trying to do is take millions of records, basically, millions of records, and do pairwise comparisons from the fields. So imagine 1 million records in a big table, and then you want to take elements of each of those records and compare fields, right? And so he was comparing those fields. And how would you do that? Well, you're programmers. You can kind of write a for loop. And he was thinking, I'll take advantage of parallelism by having a bunch of threads. So it's so easy to do threads in Java, so let's do more of them, right? That's the hammer that Java gives you, so let's use it all the time. So he had a lot of threads running and wrote his for loops and his own thread management to build this system to basically compare fields. And
that's great, it works, but you're basically modern hardware, right? One of the challenges that creates is you end up having a bunch of objects potentially thrown about in memory on the heap, and your processor is spending most of its time managing the thread state and going and indirectly grabbing data from memory, right? Modern processors don't like to do that. Modern processors, really what they like to do is like to grab whole chunks of data from main memory, pull it into the CPU, chunk on it a lot, and kind of not, and hopefully predict where you're going to go in memory, so it's loading the cache and keeping things in cache. Memory access has gotten so slow compared to modern processors that it actually have to fundamentally rethink how you program if you're going to get performance. And arrays are one way to fundamentally rethink how you program. Think about your data in chunks, columns, arrays, and then do processing on them all at once. NumPy kind of helps you do that. NumPy is an array object in Python that pushes you to write your code in vectorized format. Vectorized format is, don't think about one record at a time. Think about the whole column of data and doing comparisons that whole column of data with another whole column of data and doing that all at once. And when you do that, then it can hand that to a computer and do it very, very efficiently. And he was blown away when I showed him basically all the work he did. I gave him one line of Python code. He did the same work and was faster, turned out. And then as we add to it, so that's great. NumPy gives you array programming, but you still do want to have access to parallelism. You still do. NumPy in particular doesn't really think about parallelism. You want to have access to threads. You want to have access to parallelism. How do you do that? So Dask is a general purpose way to concurrency and have parallelism in Python code. So it handles complex algorithms. One of the things with Dask, how many people are familiar with Spark here? A few Spark users. So Spark has gotten a lot of attention in the JVM world because it scales the Java code. And it handles some problems very, very nicely. The challenge is, I see a lot of people try to shove the complexity of NumPy and scikit-learn and SciPy through the Spark straw. And metaphorically to me, it feels like you're just trying to grab this semi-truck and shove it through a little straw that's got a great concurrency model, but the API to it is not sufficient to handle the data processing volume that the scientific community has emerged. So Dask was designed to handle more complex algorithms, be a little more granular, to allow you to do, and then provide a familiar API to Python users. So it can scale. So kind of, NumPy arrays are the little subchunks. Basically, Dask allows you to create a Dask array, which is a logical, very, very large array that might have to exist on thousands of machines. Each chunk of the array exists on one machine. It does that with data frames as well. So uses pandas on each local chunk to do operations. So because Dask is reusing the scientific community stack, I'm not having to rewrite all those algorithms. It's just simply mapping parallel algorithms to the low-level chunked versions, chunked pieces. And it's co-developed these groups. So why do people choose Dask? So here's an example of an API. So you can read Parquet files from an S3 account. So what that does is it doesn't actually do the read. It sets up a transformation that begins with the read. And then as you do the operations, group by, in this particular case, by the main field, and then take the value and compute the mean. Right, so there'll be a common operation in pandas to do it on a single table. Now you're able to do it on an entire group of tables and an entire directory, and potentially, depending on what the data frame, what the Dask compute engine is, if it's distributed, it'll do that on a distributed cluster. But you have to do that compute. Without that compute, all Dask is doing is setting up a graph of tasks to compute. So before you'll see these little graph displays where the circles are tasks and the squares are data. And this is actually a screenshot during a run. There's a movie here about where blue will be, yes, I'm done with this, ready for more work, and red is I'm computing on this now. So you can basically see this graph, computing and processing. So what it means to run in parallel is you're actually scheduling a job on a bunch of machines. At the heart of any parallel computing framework is a scheduler. Often it's hidden from you, but that's the essence of parallel computing is how do I figure out what to run and where to run it. And Dask provides a reference scheduler, but also a framework for understanding parallelism. So Dask takes the Pandas API and scales it. Dask takes the NumPy array API and scales it. So very popular in neuroimaging or climate. Actually, a lot of folks in climate are using NumPy. And because of that, when Dask came out, they're really excited because that gives them access to the petabytes of data they're trying to use together. And everyone has kind of a homegrown parallelism they've typically used. Many of them are converting to using Dask and X-array. It's kind of a labeled NumPy array at large scale. So this is applicable for all kinds of data sources, and then doing high-level operation of those data sources, and having the machine do the heavy lifting for you. So, and then it's also being, added to scikit-learn. Scikit-learn has a little bit of opportunity for parallelism right now, mostly on searching for models, doing so you pick a model in scikit-learn, and then that model typically has some parameters. I need to decide a Gaussian standard deviation, or have some other parameters, a couple of parameters. I want to go figure out which parameters I should pick to make that model best predict my data. And so they call this grid searching. You just kind of go out and brute force it, look at all the different possibilities of models. Scikit-learn has a tool called JobLib that does that. It's a very embarrassingly parallel tool. Dask is now used underneath JobLib and can be used to parallelize that more easily. Lots of other libraries in Anaconda that can benefit from Dask. GeoPandas, Scikit-image. Dask scales up, thousands of nodes. Cloud computing supercomputers is actually being run on big Cheyenne 1,000-node supercomputer. It's run on clusters that get to thousands of nodes. 200 microsecond task overhead, so applicable, relatively low latency, applicable in a lot of cases. So MPI, anybody's familiar with MPI? MPI is even more low latency. So there's definitely some applications where MPI is going to beat Dask. Dask is trying to compete with it, actually. You can potentially use them together. But Dask does scale down and can run on a single laptop. So it's actually very little configuration. It comes with Anaconda, it's available to you on your laptop. You just start it up and it can run and take advantage of multiple cores on your single desktop or single laptop. So you can experiment on a single machine, and then when you get your parallelism figured out, then you can scale that out very easily, just deploy to a different environment. So that's very, very nice. As debugging support, you start up, you can actually constrain the resources, tell it if you've got GPUs working, so they can use GPUs if some of the tasks require it, and submit jobs where those GPUs are. And it's actually got some very nice dashboards. One of the real key features, kind of the hidden gems of Dask, are these bokeh dashboards. Bokeh is another tool we wrote to help make web applications with just Python code. So you're a Python programmer, you build web applications very easily without having to learn JavaScript. The author of Dask, Matt Rockland, ended up using Bokeh to build some very nice dashboards. And so you get a lot of insight into both profiling and what code's running where and how your parallelism is working, and if things are idle, resources are idle, kind of help you decide if you need to adjust how you're parallelizing your algorithm. The next project I'll talk briefly about is JupyterLab. JupyterLab is the next generation of Jupyter. The team that works on JupyterLab is working at Anaconda. They've been hard at work. It's very, very nearing completion. There's a preview release in Anaconda today. It's usable by many, and people can use it today. What it gives you is a Jupyter notebook plus terminal plus editor plus file browser, kind of everything in a web, an interactive data environment. And most importantly, it's extensible. So you can build applications of all kinds for interacting with genomic data, for interacting with image data, for interacting with data from wherever it is, bringing that together so the user can play with it. And it's composable, extensible, so you can build modern web applications easily using the foundations of JupyterLab. So it's more than notebooks. If you use Jupyter Notebooks, it usually has this, it mixes the file browser and the editor, you have a notebook, and you have a terminal. And typically people do this all in separate terminals or separate tabs, and bring all those together in JupyterLab. It's based on a Phosphor.js. If you're actually interested in JavaScript and you want to have a place to contribute, a place to dive in and learn with some really talented developers, dive in on Phosphor.js. Needs more documentation, so it's not a place for the light-minded. But if you're serious, you want to read code and be involved with a very, very, one of the best developers I've ever had the pleasure of working with, very top-notch guy, Phosphor.js is a great place to jump in. It's written in TypeScript, which is actually easier, I think, than JavaScript. So it's, in a few weeks, it'll be Userland 1.0, but it's usable now. You can run Jupyter Lab, and it'll bring up a web browser which has all these features. And you can start to play with it. And it gives you a common environment and place to do your development. Okay, so how does this work? One of the things I wanted to promote here as I talk to you all is how do we get more of this? How do we get more community, more people building together? One of the things that I've been passionate about for 20 years is building tools that make the world a better place. The way to do that is together. So how does this work? But a lot of people get confused because they think they see something like SciPy, they see something like NumPy, they see something like Dask, and they think, oh man, how do I get all that together at once? They don't recognize that it actually doesn't start that way. Everything that's been successful starts with a very small group of people, right? And then it just grows from there because it hits on a few things. So a lot of the cultivation community is one, learning, being brave enough to start, having clarity about what you're trying to accomplish, being willing to give up when it's not working, because not everything you do is going to succeed, and so that's okay. I have this sort of example just with Conda and Anaconda. These are the GitHub repositories where you see basically each of these kind of had a few people. You see this massive activity from a few people, right? But then it grows from there. In order to really achieve, you end up, and this is supposed to build out, so sorry about this, Tyler. It's supposed to just put you later, so you weren't covering everybody. But when I export to PDF, this is what happens. Tyler here we had the opportunity to work with him in the Conda team. This is where he worked. He was part of this group that helped us really make the transition in Anaconda from a group of 1 to 3 to a wider group that could receive the contributions of many, many, many. So every community I know, and I've had the privilege of being a part of many of them, has kind of worked like this. And today there's a Conda Forge community. There's 500 or so people who make Conda packages, make recipes, and there's a tool that helps test them and try them, and then they're available. Then that tool makes those binary packs available for anybody. So no matter what project you have, you can make it available for others to install and use. You don't have to wait for a set of people to approve it, or just make it available and tell people about it. So I have a couple of slides here. I don't have a lot more time, so I think I might skip quickly through this and get to.
We can extend your.
Can I extend a little bit? Oh, nobody's here? Okay, so I can go a little bit longer?
Yeah.
So one of the things I care a lot about is how do you actually cultivate community? Because I think there's some real approaches. I mean, it's not rocket science per se, it's really people science. Mostly, one thing I love is brain science. Done a lot of listening to brain science podcasts, read a bunch of lay literature and some deep literature on how the brain works and how consciousness works and how do we work as people. And there's a lot of things that, in some sense, we've learned over the past couple hundred years how to work together as people to achieve prosperity, right? To stop fighting with each other and killing each other. Now, we haven't quite learned that completely, but there are a lot of patterns that actually make that possible. And I think community and cultivating community is about resonating with those things that make us able to work with each other well. The Python community has a code of conduct that captures some of these. Remember, the Python community is open, consider it respectful. It's a good place to start. Cultivation community is really about including all points of view. One of the things that really makes especially intellectual community fester is when new ideas are not allowed to enter. And that typically is because of common, we all have our heritage, we all have our culture, we all have the things we've learned in the past. And many of those things are right, but most of those things are probably not perfect, right? There's things in I would say every one of us is not completely knowledgeable with everything we will want to learn in our lifetime. And the way to get more knowledgeable is to allow other ideas to come in. So it's really allowing diversity, but just having people around doesn't really make things diverse. It's actually listening and having communication and dialogue that makes that work. To make that happen, there's really a few principles. And all of us as humans can resonate with these principles. And in fact, if you look throughout its cultures, these concepts exist. And so I kind of sample from a few cultures in the world, and these concepts exist in every one of them, right? Because these are known ways that communities actually work together and grow. One is this concept of philia. This is sisterly and brotherly love. There's the Greek, because it first originated, I saw in Greek. But this is the idea that doing well by someone for their own sake, out of concern for her, not just concern for yourself. Kant's moral imperative was also all about this. Treat others the way they expect to be treated not as an end, not as a mean only, right? That was one way to talk about this concept. So the concept exists everywhere. So do things, if you engage with philia, if you have that concept for other people, it's key to cultivating community. You've got to recognize people as independent, worthy of being loved, worthy of being valued. Another one is seva. This is a Sanskrit word, means selfless sacrifice, sort of being willing and volunteering for the community. There's a lot of meaning in life that comes out of this, actually. A lot of the work I did in SciPy and NumPy, it really was because I found people who found it useful, and I liked the fact they found it useful. I wasn't quite sure how I'd make any money out of it. I wasn't quite sure how I'd support my family doing it. But I really valued the fact that people found it useful. And so I pursued it, continued it. At another time, I saw this just recently. Many of you know about the hurricane in Texas and Florida. Hurricane Harvey came and destroyed many, many homes, flooded homes. I had the chance to take my kids down, and we went and cleaned out somebody's house. Right? Just went down, and I did it because I want to take my boys down and have them see the benefit, how it really helps you as a person to go and just help somebody else. This concept, and it's amazing to see when you do that, how it stitches people together. Just serving people, just helping them, just doing something for somebody else. It's actually not, all of us have that natural impulse and desire. It's what allows us to join together as communities, as humans. It's a part of our makeup. Another community principle is trust. There's an Arabic word, thika, that means trust. Actually, a lot of commerce in Arabic comes out of this word trust. I love this quote from Charlie Munger about trust because I think it matches my experience as well in business and in community groups. A lot of times we try to construct guidelines, like I'm going to write all the rules and we just have to follow those rules, right? I would say that's not the highest form of interaction that can take place. The highest form of human interaction is when there's this deserved trust between people and people just work together with that trust, especially in small groups. Like this really only can exist in small groups because you can't actually trust a nameless, faceless thing. You can trust the people around you. You can trust groups. You can trust individuals. That's critical if you're going to do something together. So you have to believe and trust the people around you. And then the other thing is sustainability. It's been on my mind for a long time. You know, we have a lot of, and it's still a problem. We're having a NumFocus sustainability conference. NumFocus is a foundation I started in 2012. Data science, machine learning, so important, but it has to be connected to a bustling marketplace. When I talk about sustainability, I'm a big believer in free trade. Free trade is the foundation of prosperity and wealth. If you haven't studied that or learned that, there's a bunch of ways you can learn that. There's a bunch of literature that talks about that. It is one of the key principles of modern society that's allowed us to be wealthy. It is allowing people to do what they want, to basically build and then cooperate with each other freely, voluntarily. I think free trade plus community is the foundation of sustainability. You have to add this aspect of community to really make it work together and for things to continue to grow. Now, I've been thinking about this a long time. I'm just one person. You know, I try to act, I try to do things that make a difference, but I'm just one person, and really it's the things we do together that make a bigger difference. So I tried to create two orgs in 2012. The first was Anaconda, a company that would give jobs to people writing open source software, and then sell things in order to sustain itself. It would sell things so it could have money to give jobs to people writing open source software. And it's actually having some success doing that. Then also a nonprofit organization. A nonprofit organization basically takes donations from companies, from the world, from other people, and uses that to funnel resources to people doing good in open source. So the NumFocus organization is now a community effort. It sponsors thousands of meetups and meetups all over the world. And all this leads to kind of the first thing I talked about at the first slide, this notion of ikigai. You know, how do you actually live a life full of meaning, have a reason for being? It's a really interesting sort of Japanese group. They studied a group of people that were living well into their hundreds in Japan. And kind of why were they living so long? And they found that that group sort of practiced searching for ikigai, this reason for being. This reason for being gave them a reason to get up in the morning, gave them a reason to do something. And it's what led fundamentally to longer life. Longer life, how you exercise is important, diet's important, certainly not getting in an accident, not having violence. All those things are critical for you particularly. But important, all those other things held constant, is actually caring about what you're doing, having a reason for living. So if I look at my life and I think of these circles, what you're good at, what you love, what the world needs. I found as a grad student, working in the Mayo Clinic, I found that I was good at programming in C, and I could make C APIs for Python. I found that I kind of loved doing that actually, making libraries for helping people, connecting 4chan libraries through Python and sending it to the world. And it sounded like the world needed that too. And it seemed that seems to be true. However, I wasn't being paid for it. And a lot of my friends weren't being paid for it either to do this. And so we kind of had that all what you're good at, the world needs what you love, all kind of together. So there's delight and fullness, but no wealth. Right? So that doesn't really last. It can't last very long. Or it can last if you have somebody paying you, I guess. If you have a really, a sugar daddy or a rich uncle or a rich aunt, somebody just providing money, I guess that could work. So a lot of what I've been doing over the past 10 years has been trying to figure out how to help me and others like me get paid for what I love and what I'm trying to make the world a better place. And you can see some of the, when you lack one of these, if you're lacking what you love, then you end up you might be comfortable, but you have a feeling of emptiness, you can't do what you love. So combining these, I think right now especially, when you're exploring life, exploring what you're good at, exploring the things around you, I think think about this, think about, ponder it, try to understand how that makes a difference in your life. And this will change throughout your life as well. But as you contemplate that, I think it really can make a huge difference in becoming and living a life that's full, living a life that you're thrilled with, that you're excited about, that makes you makes a difference. It makes a difference for everybody around you. Tell a little about my journey to find Ikigai, right? I said a little bit about it, but I really love science. My love of science kind of led to these distractions. Like I was on a career track to build, I really wanted to build a better way to measure glucose for my diabetic niece. Right? I wanted to figure out how to build a system that could monitor glucose and help her and help others like her. Didn't end up going that direction, although those systems are coming out now, not because of me, but because of other people doing that good work. I wanted to figure out how to make the world a better place. But doing that, I was actually, okay, maybe I'm a little better at computers than I am at lab work. And so it kind of led me to do more SciPy and NumPy work. And I ended up doing a whole lot of science, but that science led to Python. And that Python then led to all this exploration with community and all this exploration, trying to find Ikigai in my life. Many of you don't know the origins of Python. It's been around since 1991. This is Guido van Rossum. He wrote it as a teaching language. I started using it in 98. So I used 1.4 was the very first version of Python I started using. Yeah, so I've experienced all the pain of Python's growth. And I wrote C extensions, so I experienced the pain at a very fundamental, deep level too. So you don't have to experience that pain anymore. The other thing I like to point out is the very first thing I did was write an extension in 1998 that was inspired by a guy named Michael Miller. He was actually, I think, at the University of Illinois, I think, now that I recall. I should look that up. I didn't think about that before I came. But he just released something, he gave it to the world, gave Table.io. Hey, this is something I did. Well, that was really important for me because I looked at his code. It was important he released it. I looked at his code, saw what I kind of learned from that, how to do NumPy.io, which was my first released module in June of 1998. So I borrowed heavily from the work of others because they published their work, because they let people know about what they're working on. They let people know, even though they hadn't solved the cancer, they didn't have something amazing, they just shared what they were working on. That's how come I got to love the academic ecosystem, the academic world. SciPy emerged really in 1998. It's coming upon the 1.0 release now, 19 years later. It's finally becoming 1.0. I just got a note. I haven't been deeply involved since 2009, for about 8 years. But for a long time, SciPy was really the thing I cared deeply about. And I wrote a lot of things to help that emerge. This is the year that I couldn't tell my wife till later when I had a job and she wasn't, with 3 kids at home wondering when I actually make some money. Soon we'll be out of debt. Right. But that's okay. The things you learn, actually at an early age, just exploring the things you love, you'll reflect back on and love the rest of your life. SciPy came out in 2001. really is a combination of the work of a group of people. We kind of brought our stuff together, and SciPy itself wasn't named until 2001. The first release of the bundle of packages I've been working on for a number of years was in 2009. Of course, SciPy then led to it was built on numeric. NumArray came around and was threatening to break the ecosystem apart. And so, as a professor, I felt that I had an opportunity, and so I felt it was my duty. Wasn't good for my career as a professor, but I needed to work on NumPy to bring those communities back together. I did that in 2005, released in 2006, where NumPy came from. But it really built on the shoulders of giants. Jim Huguenin, Paul Dubois, Perry Greenfield, Rick White. These are the people that led to the precursors to NumPy. They were very, very critical for the success. I could not have written NumPy alone, kind of just de novo, without the work that they had done before. And now it's a very impressive community effort. There's actually 561 contributors to NumPy, 534 contributors to SciPy. This enormous communities have risen, and that didn't happen overnight. It actually took some time. And then since 2007, I've been making the transition from academia to industry. My goal really being, how do I get paid, how do I help others get paid to produce these key open source tools? And that's been, being able to do that has kind of transformed a little bit. So I don't write the tools anymore. What I love is to help people write tools and then help inspire them, help guide them. A little bit of inspiration here and there what the tools should be, at least presently. Maybe I'll write a tool or two again in the future. And then really building an ecosystem. That's the thing that's driving me now. How do I build an ecosystem around Anaconda that allows these tools to continue to grow and flourish and encourage others to build companies and ecosystems and communities themselves that satisfy and help them find ikigai in their life. And at the core, embracing sustainable commercialization. I'm not one to shy away from selling things. You have to sell things to live in the world. So the key is, how do you sell things in a way that's consistent with community? That's consistent with growing infrastructure that's open source and helping people succeed together. How do the ecosystem is exploding? This, I'd like to point this out because it's still emerging, and it's all over the world. One awesome thing about being involved with this ecosystem is I get connections from all over the world of people. I kind of have a community, I have a home. If I go anywhere in the world, I can kind of look up the local PyData group, and there's people that we have a connection, even if it's that small. And that part of that connection is enough to start building friendships that last a lifetime. So a couple of final keys to success as you start on your journey in life, your journey of building, creating, finding ikigai for yourself. One, hard work. It doesn't happen overnight. There's a lot of failure between something successful and something starting. And a lot of ups and downs and a lot of difficult times. It's actually often very lonely. Nobody believes you at first. When I said I'm going to write NumPy, I had a lot of laughs actually. People were like, I don't see how you're going to do this, because you got this community split, it's like hard code base, it was numeric, I had to join stuff together, release a bunch of C libraries. For about 8 months, nobody really joined me. I was pretty much alone. And then finally, as people said, hey, this might work actually, I got people jumping in and they were helping. But it takes a lot of lonely times. And the more complicated you're doing is, the lonelier it'll be initially. That SciPy, there was a conversation in 1998 on the mailing list. People said there really ought to exist optimization libraries for Python. They could see the vision, they could see where it was. Somebody had to put the effort into it. Now I happen to have some volunteer time. If I had been now in my career, I couldn't have done it. I can't take a year off of my life right now and go spend working on something like SciPy. It's sad, but I couldn't do it. Then I could. I had enough room. A good enough relationship with my wife, good enough relationship with my kids, enough coming in. I had a stable stipend from the fellowship I was receiving, so I had something. I wasn't poor. I wasn't eating dirt. Didn't have a lot, but I had enough just to do that. So I procrastinated a PhD and then started SciPy, and that built a community of people around it. Right? It often just enough to do that. A lot of other people did too. P.R. Peterson. A lot of people have done things right. Another key to success, I think, is do what's right, not what's convenient. Timing is everything. Sometimes you are the right person for the job. I think that's an important question, only something you can answer. In this particular case, NumPy, I realized NumPy I wanted it to exist. I knew it should exist. I couldn't think of anybody else who would or could do it at the moment. I just wanted to build a bunch of C extensions for Python, knew the numeric API better than anybody. and I had time as a professor. Everybody else I knew was busy in their jobs or wasn't really aware of how the functions worked. You have an urgency, won't wait, so doing it, and then strive for excellence. And the other thing is, I love this quote from Mother Teresa because give the best you have will never be enough. They'll forget about the good you did yesterday, and they will. But do it anyway. And then finally, you can't do it alone. The key is to gather people around you. And that means, somebody will point out you suck. And all of us do, in one way or another. None of us are perfect in every way. So someone will point that out, and that can be hard. I'm no different. When people tell me I suck, I don't particularly love it, but it's true usually. And so listen to them. Listen to them. Nurture empathy. Treat people like they matter. Build those principles of community. And then build good luck. And this is actually key because if you're not finding the good luck, sometimes you have to restart and redirect, do something else. Have other stories about that. So I'll end with what will you do today? What will you do? Taking the information you have, you're in a unique position in your life, you're in a unique position in the world. You're right now studying at a great university. It's a fantastic university. You've got resources available to you that millions of people would love to have access to. You have ideas, you have data, you have connections. What are you going to do with them? You have to think about what you're going to apply. You have to trial and error, and you have to do it together with people that matter to you. So I encourage you to do it. Go out and build something fantastic. The world's waiting. Thanks.